So we just heard about some actual things Ralph has been doing, which is more sophisticated and hopefully, ultimately, productizable version of what Ted Sanders and I did in a prototype format just a few years ago.
I don't know how we became all students through the lecturers.
Yeah, what I wanted to discuss, you can feel free to stand up and mob around the microphone.
I'll just put the microphone in between people. All right. Okay.
Yeah, what I wanted to plant in people's minds next was sort of the question and some general ideas about how to use neural networks for action learning. And so what Ralph is doing now is perceptual pattern recognition, and the use of WaveNet he described, in essence, it's a kind of imitation learning, right? I mean, it's an abstract form of imitation learning. You're trying to look at head movements and then imitate that, and that's a particular kind of action learning. But ultimately, especially when we have arms moving and robot rolling around or walking around, we want to use neural networks for
the arm animation, certainly.
Yeah, but we want to do reinforcement-based action learning. So if the arm is actually doing something, like if you want to make an arm hand something to someone, or just pick something up and show it off, right? Then you have a situation where you have a reinforcement signal from physical reality, and then you can use techniques from the general area of reinforcement learning to train the neural network, and that's hard to do with like smiling or frowning, because the reinforcement is very high level, right? I mean, you smile, someone may smile back, but you're not getting ever detailed feedback about the corners of your smile. It takes a lot of trials to fine tune your smile based on feedback from other people. I mean, that probably can't happen. People who are good actors probably do that. I don't think I ever have. But if you're doing reaching and grasping, there's pretty fine-tuned feedback on what happened and why. When you dropped the object, when you moved, how far away from the object you were trying to pick up, and so forth. So what?
I'm sure actors look at mirrors.
Yeah, probably.
And if they're not looking at mirrors, they do look at how they got filmed in front of the camera. So they're aware of that.
I used to hate mirrors. I spent 15 years without looking in the mirror. And I finally looked at myself. I was amazed I changed into a totally different person. That was before you were constantly looking in your camera and looking at yourself. Yeah, so one architecture which I've seen others take for deep reinforcement learning is to have two neural nets coupled together. So you have one neural net that's doing reinforcement learning, and there's Q learning, and then there's other more sophisticated algorithms for that. Then you have another network which is building a deep hierarchical model. So one thing that I've seen which is kind of interesting, you have a reinforcement learning network that basically it takes inputs to outputs. So it could take sensation about where visual sensation about what's near the hand, and feedback from the hand's own actuators, and then you feed that into the network, and the output is movement commands for the arm and hand. So you have.
So this is learning to pick things up here.
As one example, yeah, learning to grasp something, right? Learning, reaching, and grasping. So one thing I've seen there is you take a reinforcement network that learns reaching and grasping, and you couple that reinforcement network with a multi-level deep neural network whose goal is to build a hierarchical model of the state of that reinforcement learning network. So the state of the reinforcement network is fed as the inputs to the deep neural network, and then you backpropagate through all of these things. So basically the fitness function of the deep network is how well can it reconstruct the state of the reinforcement network. So what you're doing there is you're doing reinforcement learning, and you're in essence imposing a bias toward connection weight sets in the reinforcement network which have a hierarchical model. And that's sort of interesting, and it seems to be a good bias. Like, it seems to work better than just using a reinforcement network, because it pushes you to learn certain classes of weight sets there. And that has a lot of interesting aspects, because once you have a hierarchical model to what the reinforcement network is doing, you can then try to correlate it with the hierarchical model of visual perception, whereas it's hard to correlate the states of the reinforcement network directly. So that's something I thought was interesting. And then that reminded me of Dave Damaris's sort of coupled map lattice framework that I asked him to give a brief talk about tomorrow morning, because you could do something similar there if you used a coupled map lattice for learning movements, like in place of that reinforcement network with Q learning, say you evolved a coupled map lattice with a floating point GA to take certain inputs into certain outputs, then if you co-evolve that with a hierarchical neural network, then you're sort of learning the parameters of the coupled map lattice, and you're biasing it to parameter settings that will make the overall state of the thing have some hierarchical structure, which you can then correlate with hierarchical perception and so on. And that would be one step further in the direction of weird experiments, but it's interesting to think about. So I think this...
I mean, but I'm thinking in terms of just demos and practicality in the next small number X months.
Yeah, then this is irrelevant. I don't think we're going to get this working in the next 3 months.
Well, sure, but you're also talking about very complicated things, and for demo ability, you just need her to have hand gestures while she talks,
yeah,
and the ability to wave hello, wave goodbye.
Yeah. So if we wanted
type
if
gestures,
we wanted to
you don't
do
have
that,
because grasping is hard. And,
yeah.
And so you're pursuing that, but before we do that.
Well, if we want to do that using pure imitation learning, then what we need to do is get motion capture working on arm movements, right? So if we had a motion capture database on arm movements, then we could take the same approach we're taking now with WaveNet for head movements. I mean, if you're just looking at gestural arm movements, I think the same approach could work. So that just, I mean, face shift is for faces. We don't have arm shift, so we'd have to, I mean, but there are...
It would make David very happy.
There are mocap studios all around here. I mean, Gino has one at PolyU, and there's a bunch of others. So, I mean, they have like, Gino has 6 cameras from different directions. So, I mean, if we had someone do gestural movement in a mocap studio...
I've talked to David about it.
Yeah.
Bit,
I mean, then we could do that using the same WaveNet-based infrastructure. So I think that's not a huge research challenge. That's
it's not a research
just
challenge.
That's just doing it, right?
Yeah,
so,
I'm focusing on.
Yeah. I think
X for a small x. Right?
Yeah, I think the main step there is actually getting the motion capture setup working, and then recording that data. Like, Gino did this for some Jackie Chan Kung Fu video games. So he had people go in the mocap studio and do a bunch of Kung Fu, and then they use that to drive the Kung Fu characters in some Jackie Chan video games. And that was much harder than waving your arms around expressively, I guess. Maybe we can get that data and make the robot do Kung Fu too. Although wheeled-based Kung Fu is its own weird discipline.
Maybe more
There's
like
a lot of whirling around stuff.
Sufi, the Sufi robot.
Oh yeah, sure. Being a whirling dervish with a wheeled base is pretty easy. We could simulate making it get dizzy when it whirls around. Like, put some gyroscope in there and tie it into its one emotional system. Right?
If it gets too high, and negative valence goes up.
Yeah. Well, if you put
It's going to get a gyro just to have it go in a straight line.
Well, if we
so
put the
don't
right
have a
chemical
gyro.
sensors in, you can make it get stoned too, right? you detect the THC molecule in the air, then affects it. It can get secondhand stoned.
Nice.
But how are hand gestures possibly different from facial expressions? Because I think if you think about hand gestures, like we do a lot of high conceptual.
Well, what I saw
more
in this Clockenflap performance was that random arm gestures on with roughly the right timing, roughly the right rhythm, gave everyone, including me,
That's true.
the delusion that she was moving her arms emotionally while she was singing. So I think if you just get a little bit of actual expression in there, then we're willing to interpolate the rest. I mean, just from an immediate practical point of view. But yeah, you can see, like if you have an arousal variable, right? If the arousal variable just corresponds to a bigger amplitude of arm movements, then that gives you something, right? And then, I mean, if the anger variable corresponds to clenching the fist, and then you could have record like a half hour of different fist clenching movements. Then you train a neural network of fist clenching. So then when the robot's angry, then it generates a movement from the fist clenching neural network. So I mean, I think if you made an ontology of a dozen categories of gestural movement, gathered mocap data for each of those, trained a model from each of those, then that becomes quite similar to the head movements once you have the mocap data gathered.
There's a sequence of motions that comedians do when they go on stage to greet an audience.
Yeah.
I remember seeing them. One of them is called the refrigerator pull.
Does this elicit a feeling from the audience?
Yeah, no, it's if you watch them, they'll do this, but they do this kind of like, hey, Elvis used to do this, hey. But a version of that is you don't push out the two hands. I really like you guys.
We did get a request from Graceland to make a robot Elvis.
Whoa.
Hasn't been followed up on yet. Yeah, I think that's a good idea. Yeah.
Which Elvis though?
They weren't clear on that.
Ugly fat one.
Yeah, if we get to choose.
Yeah,
sounds
we can
fun.
you can use the map oscillators for the pelvis oscillation. It's the right periodicity and chaoticity mixed up.
All is love. Come on, man.
Yeah.
Oh, Elvis. Never mind.
Yeah. All right. I think if we had the whiteboard, I could go in more detail. But as Linus says, that's reinforcement-based movement learning is a little ways off. But I think the architecture that we'll build for embedding this hierarchical neural net into OpenCog and recognizing patterns in it and so forth, that same architecture you could use if you had a reinforcement net coupled with a hierarchical net for movement learning. Then that hierarchical portion of movement learning would have a similar form to the hierarchical network for vision. But that's it. I mean, I would love to do this for walking, for example, walking with dynamic stabilization is a hard problem. You typically do that. You can learn the walking movements connecting to Gazebo or some other robot simulator. So you have a lot of reinforcement feedback symbols of like, is the thing falling down? How fast is it walking? How stable is it? And so forth. So that walking in a simulator is a good problem for testing this sort of thing. I mean, not immediately that relevant because we're starting with a wheeled base, but there's the intention to put a walking base on eventually. And then similar to with all these other movements, you can either sort of hack walking by some combination of just solve the Lagrangian and then tweak it a bit to make it more human-like, or you could try to do something fancy such as we've been describing.
What about more higher level action selection for like, go bring me the red ball?
Well, that's, I mean, in the OpenCog framework, that's more like a PLN planning type thing, and then the high-level plan has to invoke lower-level movements, right? So like to go bring me the red ball, first of all, which red ball, right? Then once you found the red ball, if you want to go there, yeah, somehow you have to decide, do you turn and then walk that way, or do you plot some continuous arc to get there, right? And that sort of movement planning, yeah, that's its own problem, which is different.
Well, there's personality in there too. I mean,
actuators.
you just illustrated. I mean, I have known geeks who, if you say that to them, they'll do just what you did. They'll do it, and then they'll walk. And
So
fluid people.
Xu Jing, as part of her thesis, like Xu Jing wrote a paper that on how to combine planning and navigation in OpenCog. So she built a planner that it does navigation sort of at the level of A*, standard navigation algorithms are better, but it does navigation kind of interleave with planning, which means that if you need to go from here to there, but there's a gap and you need to like build a bridge across the gap or something, the planning to get a bunch of blocks to build a bridge across the gap is done in the same process as the path planning for navigation. So she sort of showed how planning and navigation can be interleaved in the same recursive graph-based planning algorithm. That was done in the video game world though, like in the Minecraft type world. Now that planner is stuck in some archaic, widely diverged branch of OpenCog, and the code of that planner isn't really what we want because it doesn't use the OpenCog rule engine. So it's sort of its own special C++ rule engine. But the concept there of how navigation and general planning are interleaved, which is in a paper we had published last year. I mean, I think that concept is correct and could be replicated in the URE, basically by putting some...
I thought it said something like it's an A* search 3D algorithm thing. Is it more than that?
Yeah, it's more than that because it does inference and A* search in the same process. So if you're doing A* search and you get to a river, A* can't figure out how to build a bridge over the river with blocks, but Xu Jing's planner does that. So it combines sort of backward chaining based planning with navigation, which conceptually makes sense because I mean A* is just a chaining based planning in a way, but people have never done those two together in the same algorithm before. That was a novelty of it. But the problem is she did it by implementing a specialized planner in her own special rule engine.
Yeah.
And so, but if you implemented rules for sort of atomic navigation, you pretty much would need a rule for find the most promising looking spot and go there, right? And then that invokes some primitive movement planning to go to some visible spot, right? If you implemented a rule like that and put that inside the current chainer, I think we could replicate what she did there.
Yeah, with some tailored inference control.
Yeah, the other thing is the inference control makes use of time, right? So you sort of in that planning algorithm, you figure out what to do first, then next, then next, then next. So you're instead of searching for all possible combinations of actions, you're searching for combinations of actions by finding one thing, then the next, and the next, and the next, and the next, or working back from the goal. So here's what I want to do. What would I do before? What would I want to do before? What would I want to do before? So that's using temporal sequence to prioritize what inferences to do, basically. Yeah. So if you made in the simplest case, if you made a custom control algorithm that just stepped forward from the beginning and backward from the goal in time, and you had a primitive operation for how to move from one point to another visible point, then you would be doing what Xu Jing and I described in that paper, what her code does. I mean, since our robot doesn't move at the moment, enhancing robotics hasn't been a priority, but once the robot rolling bodywork, so it'll actually be interesting to do. And so like if there's a lightweight cardboard box in the way or a person in the way, then it could roll up to them and bump the box out of the way, or it could say, hey, get out of my way, I'm trying to get over there, right? And so then those are actions that an A-star navigation algorithm wouldn't do, but the planner can do. Then once it's made the annoying person or object get out of the way, then it resumes basically inference steps that are equivalent to A-star planning.
Yeah. I mean, you do need a tailored inference control mechanism so that you take advantage of the assumption that whenever that you don't have to backtrack essentially.
There may be a tailored importance spreading mechanism. So after you were thinking about
maybe yes, a tailored fitness.
After what you were thinking about at this point in
Yeah.
time, what becomes
Absolutely.
next most important is the immediate times before and after.
Yeah.
Then those have highest STI,
Yeah.
and then the selection is biased toward those atoms, right?
Yeah.
That would be a sort of slick way to do it.
Yeah.
All right. I think that is all I had to discuss today. Anything else from anyone else?
Can you demonstrate more of that kung fu?
Mike can demonstrate Tai Chi, right? But he doesn't want to. So. All right.
Wow.